Okay, welcome back. Let's roll into the big rectangle. As I said last time, any test in the big rectangle, no negative terms enter the big rectangle. As you enter the big rectangle, if there's a -1 to the n or n plus 1 in your series, it's taken from you. Okay, like big rectangle security is just like NO, confiscated. I'm confiscating your negatives, right? They all leave. Okay. So once I'm in the big rectangle, I am testing for what is called absolute convergence. My computer will listen to me. Okay, now, absolute convergence means something very specific in math. It doesn't mean like, oh yeah, that thing converges, absolutely. Like it doesn't mean like, yeah, I'm sure it converges. That's not what it means. The word absolute comes from absolute value. Okay. So if we are testing for absolute convergence, or if we say we have absolute convergence, what we mean is that we tested the absolute value of that series and it still converged. Okay, now think about what that means, right? If I have a series that had negatives in it, half of my terms were being subtracted. When I push it into the big rectangle and I throw away the negatives, all those terms that were being subtracted are now being added. And it still converged. And remember, convergence means it didn't go to infinity. So all the terms that should have been taken away, instead of taking them away, I added them back. And it still went to a finite value. That's called absolute convergence. And the fact is, if a series will converge absolutely, if a series will converge after you took its negatives away, it certainly will converge if you give back its negatives. Okay, so if you can prove that a series converges absolutely, you've proven that the series itself converges. Because if I take the negatives away, all I'm doing is making the situation worse as far as approaching infinity. If it still doesn't go to infinity, even with the negatives gone, I have absolute convergence. And if the absolute value converges, then the series converges. Okay, it does not work the other way. If the absolute value of a series diverges, I don't know anything about the series itself. There are some series, their absolute value diverges, but if you let them have their negative, they'll converge. Okay, and we'll talk about those series. But if you want to be in the rectangle, which is where we are most of the time, you are looking at absolute convergence, so you should not have any negative terms. Okay, so I want to just show you a couple series here. Okay, so here is a series, -1 to the n over n squared. So -1 plus 1/4 minus 1/9 plus 1/16 minus 1/25 plus 1/36 minus 1 over 49, and so on and so on and so on, right? This has negatives in it, right? Well, we'll get to this in a minute. I want to know if this thing converges. It has negatives in it. So I say, okay, well, is it geometric? No. Is it a p-series? It's kind of pushing it on account of a p-series is just 1 over n to the power, doesn't involve any negative ones, right? Okay. Are the terms approaching 0? Yeah, the terms are approaching 0, so I can't use nth term. Okay, so got to go into the big rectangle, right? Okay, so I push it into the big rectangle. I throw away the -1 to the n. When I throw away the -1 to the n, this is the series I'm left with. I'm left with 1 over n squared. In other words, I just pitched the negatives. So now instead of alternating signs, I have all plus signs. So now I'm in the big rectangle. I'm testing for absolute convergence. And I look at this and I say, oh yeah, this converges. This is a p-series, right? This is a p-series. P is greater than 1. This converges. Because the absolute value converges, I can come back over here and say, yes, this series converges absolutely. That's what we say. This series converges absolutely. It has absolute convergence. If I took away its negatives, it still converges. So this is the series that goes into the big rectangle and gets tested. Okay? And I can use any test I want once I'm in the big rectangle. Okay? So technically this isn't a p-series, but its absolute value is, and once its absolute value, once we know its absolute value converges, we know it converges. Absolute convergence. That's really, really important. We're going to talk about a different kind of convergence soon enough. Okay, so into the big rectangle we go with no negative terms. I just want to say, before I even talk about the direct comparison test, I just want to apologize to you. I hate this test. It's a lot of talking. It's a lot of explaining yourself. I don't use this test unless I absolutely have to. And I'm going to tell you why. 2 reasons this is my least favorite of all the tests. It is what we call a comparison test. A comparison test means that you have to come up with another series out of your own brain to compare it to. And the series that you come up with has to be similar to the one you're testing, because after all, you have to be able to directly compare them to one another. But also, by the way, the series that you come up with out of your brain, you have to know its behavior. So you have to know if it converges or diverges. So first things first, before I can even begin to use the direct comparison test, I have to look at the series in front of me and come up with a series that is similar to it, but whose behavior I know. I'm annoyed already. I don't want to have to come up with my own series. Okay, oh yeah, also no negative term, but we already knew that. Okay, so this series, does that converge or diverge? I don't know. That's not a geometric. It's not a p-series. It's not an nth term. That's the terms are going to 0. I got a factorial in the denominator, right? This thing's going to 0. The question is it going fast enough? Okay? I have an inkling, but we have to prove it. So for direct comparison, I need to find a series that's similar to this. Here's my strategy. When I look at a series and I need to come up with something to compare it to, I think, okay, if you were going to infinity, I think back to like when we did limits as approaching infinity, and we would start saying like, +5, who cares? Oh, this sign, what's that ever going to be? A 1? Who cares? Right? And I rewrite my series without all the who cares things, right? So I look at this and I say, okay, sine of x, what's that ever going to be? Some number between -1 and 1? All right, well, watch me write this new series, 1 over n factorial. All right, now this is going to be the series I compare to. So I've come up with a series. Again, coming up with a series is no easy task, right? Now, I will tell you, we'll prove it later. I will tell you, and I probably don't have to tell you, that this converges. 1 over n factorial converges, and it does it fast. Okay, so if my series converges, that means that these terms are getting small enough that this is approaching some finite sum. So if I can just prove to you that these terms are smaller than these guys, then this must converge, right? If these terms are little enough to converge, if these are even smaller, it has to converge. Okay, so this is the second reason I don't like this test. Now I have to like write out an argument. Anytime I have to explain myself, I'm not happy. Right? They always say on the AP, if you're writing more than one sentence, like you're doing it wrong. When I start trying to explain myself, I find it very difficult to just get that into one sentence, and then I feel like I start talking myself out of a right answer. Okay? So for this one, we would have to explain why we believe that the sine of x to the x over n factorial is always going to be less than 1 over n factorial, right? And that's not a terribly difficult argument in this case, right? All I have to do is explain why this is always going to be less than or equal to this, right? And we know that sine is always going to be between -1 and 1. So the biggest this could be would be some power of 1. And we know that if it was 1, it would converge. And that's the biggest it could be. Probably it's going to be smaller, and some of your terms are going to be subtracted. So since we know this converges, we say this one converges by direct comparison. But again, you have to come up with your own series, and then you have to convince me that if your series converges, that this one is always smaller. The other option is to prove divergence by saying, okay, well, I have a series that diverges, like let's say 1 over n, that diverges. Okay? If I'm comparing that to something like if I have a series like 2 over n, okay, well, if 1 over n diverges, 2 over n has to diverge because it's even bigger. Right? This is too big to converge. This is obviously too big to converge. It's precisely twice as big. The problem is, again, with direct comparison, you kind of already have to know where you're headed before you do anything, right? Because if I want to prove that this series converges, then I have to come up with a series to compare it to that converges. If I want to prove that this diverges, then the series I come up with has to diverge. Okay? If I pick a convergent series and I can't prove that it's smaller, I got nothing. If I pick a divergent series and I can't prove that it's even bigger, I got nothing. So you pretty much have to look at the series and use your infinite intuition to say, I think that's going to converge. Let me find a convergent series to compare it to. I'm going to tell you, unless it's something very simple like this, we almost never use this. Right? And AP is not going to directly ask you, direct comparison, it's 3, to use this test. Now, there are other tests, and I will let you know that they can ask you specifically to use. This isn't one of them, right? But it can be a quick one, like, okay, this converges, especially if you can use the harmonic series or something. But again, least favorite test ever, direct comparison. Least favorite. Okay, let's look at this series. I kind of already said this. So they give us the series, is 3 over n converge or diverge. This is the type of situation where I would use direct convergence, right? Because I'm going to say, okay, 3 over n, that looks an awful lot like a friend of mine called the harmonic series, right? This series, 1 over n, which is 1 plus 1 half plus 1 third plus 1 fourth. I know that diverges. And check this guy out. He's 3 times that. Right? So he's 3 plus 3 over 2 plus 3 over 3 plus 3 over 4. Term by term by term, each one of these is bigger than each one of these. So if he diverges too. Okay. 2 as well. Okay, so this is the kind of situation, a very simple situation, a very straightforward one, where I might use direct comparison, right? I might say 1 over n diverges, 3 over n diverges by direct comparison, something like that, right? And again, this is not going to be one that we're using a whole heck of a lot, right? Now, one they can ask you to use is this one, limit comparison. So when we write this one on our chart, we're going to put a star next to it because AP can ask you specifically, do this using the limit comparison test. God, I hope they don't. Okay. Not a huge fan of limit comparison test. The limit comparison test is just a very technical version of direct comparison. So what the limit comparison test does for us is it takes one of the evils away, right? I still have to come up with something to compare my series to, but once I come up with it, instead of having to explain myself, I just get to like do this limit and then interpret my result, right? So I don't have to write words. I don't have to explain myself. But again, I still have to come up with something to compare it to. Here's the deal. Okay. There's really, what you do is you take the term from your series that you have, that you're interested in, and you take the term from the series you made up to compare it to, and you put them in a ratio. Now think about what that means, right? If you take a ratio out to infinity, one of the things that can happen is you could get a 0 for your limit, right? If you get a 0 for your limit, what that means is that this guy grew faster than this guy, right? Because as I approached infinity, this thing got small enough compared to this thing that this quotient approached 0. Okay, so what have I proven? If I get 0, I've proven that this is smaller. So look at what this says. If you get 0 and B converges, right? So this is the one I'm using to compare it to. If this converges, now I've shown that this one is smaller, then it'll also converge, right? That's what we did with direct comparison. Right? We said, we just proved that it was smaller in a different way. Okay, this actually, you put it in a limit. So you put your series of interest on the top and you compare it to the one you chose. Okay, if it comes out to 0, that means the one on top is smaller and you have convergence, as long as your series converges. Now, another thing that could happen is that it goes to infinity, right? If it goes to infinity, that means the exact opposite thing. If it goes to infinity, that means that the one on top was bigger. So now if it goes to infinity, I know the one on top is bigger. It had to have gotten much bigger than B. Okay. So if the one on top is bigger, then in order to prove anything, I have to know that this diverges. Okay. So if this diverges and this is even bigger, then I have divergence. Okay. If you get a 0 and this guy diverges, fail. If you get an infinity and this guy converges, fail. Which is another reason I like this test. This is a lot of criteria to remember. And it's 50-50. It's going to work out for you. Right? The last possibility is that when you put them in a ratio, you get some constant number. And we learned way back when that if you do a limit to infinity of a quotient and you get a constant, that means these guys are growing at the same rate. Remember that? So if these guys are growing at the same rate, then they either both converge or they both diverge. That's the best thing that can happen with limit comparison. Because that way, if the bottom diverges, so does the top. If the bottom converges, so does the top. Okay? Otherwise, you always have to know the behavior of this. But whether it goes to 0 or infinity is going to determine if you can do anything about it. Okay, now again, I don't memorize this stuff. For me, it's more of let's think this through. If it went to infinity and it went to 0, that means the top must have been smaller. So I just proved that my series is smaller than that guy. So I can only prove convergence if I have something smaller. If that thing goes to infinity, then I know I have something bigger. So if my thing is bigger, then I'm only going to be able to prove divergence. Okay. Again, they could specifically ask you, they reserve the right to specifically ask you to use limit comparison test. We don't really see it very often though. Okay, so here's our old friend, sin x to the n over n factorial. Right. So again, limit comparison test, we have to come up with something to compare it to. Now we already decided earlier that, we already decided earlier that we were going to use 1 over n factorial, right? All right, so let's set this up. I'm going to do the limit as n approaches infinity. I'm going to put the series that I know on top. So I'm going to have sin x to the x over n factorial, and I'm going to divide it by the series I want to compare it to. I'm going to do this limit, see how it comes out. Now, I know this converges. Right? This guy converges. So what I'm trying to show is that this is smaller. Right? If this is smaller, I'm all set. If that's smaller, this better come out to 0. Okay? Or if it came out to a constant, I'd be happy because that means they have the same behavior. If I get an infinity out of this, I'm in trouble because all that means is the top is bigger, which means nothing. So let's see. I know how much you love simplifying a fraction in a fraction, but I got to tell you it's going to happen a lot in this section, so get used to it. I would like a different color. Okay, so look at what I have here. I have something divided by n factorial, something divided by n factorial. These guys just cancel. See you later. All right. So this ends up being the limit of sine x to the x. Again, look, this is approaching infinity. This is oscillating between -1 and 1. So here's what I have. As n grows, I have a number oscillating between -1 and 1, and it's being raised to the infinitieth power. Okay. Is that going to go to infinity? No, because these numbers they're little, right? They're between -1 and 1. They're oscillating back and forth, so you're adding some terms, you're subtracting some terms. So it's not going to 0, but it's not going to infinity either. What's happening here is you're going to have constants the whole time. So there's never a time when this limit isn't going to produce a constant. So because it's a constant, we can say they have the same behavior, therefore this guy converges. So it's sort of like direct comparison, but like I said, you just do a limit and interpret the limit instead of writing out and creating an argument. These are both stinky tests. Any test that requires me to come up with my own series, I'm not a fan of. Okay. Let's do another one anyway. Let's say they force us to do the limit comparison test. They say, use the limit comparison test to discuss the convergence of this series. All right, so look, this is what I was talking about before. If you need a series to compare it to, think infinity, right? I'm going towards infinity. If I'm headed towards infinity, what kinds of things don't I care about? I don't care about +1s, right? So if I'm headed towards infinity, I'm going to pitch this +1 and this +1 and then slim this thing down to 2n and then n squared, right? At 2n and n squared simplifies to 2 over n. Okay, so this, for me, is a good series to use for comparison because it's similar enough to this. The only difference between this and this is these little +1s. And we know that as we approach infinity, those +1s don't matter. So whatever this series is doing, this one's probably going to do the same thing. Right? Now, I already know what this series is doing. Because this 1 over n is p series, right? Which diverges. And 2 over n is even bigger than that. So this guy has to diverge. Has to. Okay, so here's what I got to do. Put them in a limit together. See what happens. The series I have on top. Series I created on the bottom. Now, if I can get this to come out to infinity, I'll be happy because I have divergence here, so I've then proven that this is even bigger, divergence. Or if I can get this to come out to a constant, I'll be happy because that means they have the same behavior. All right, let's see what we can do here. Again, we're approaching infinity, so the first thing we always do when we're approaching infinity is get rid of the stuff we don't care about, right? So if I'm approaching infinity, this +1 doesn't matter and this +1 doesn't matter. So I have 2n over n squared on the top, and then this guy, I'm going to invert and multiply. Get rid of the fractions. And what I have, n squared over n squared. So I have the limit as n approaches infinity of n squared over n squared, which is 1. Okay, so we were right. These +1s, who cares? Right? This series and this series are going to behave in the exact same way, and that's what we've just proven. So I got a constant out of the limit comparison test, which means that these two are growing at the same rate. If this one diverges, this one diverges too. So we say diverges by limit comparison. Okay. One of the things that you have to do when you're on the AP is you always have to state the test you're using, right? So if they say use the limit comparison test, obviously you don't have to say I'm using the limit comparison test. But if they don't, then you want to say by the limit comparison test, this is what I have, right? So we would say, okay, limit comparison test, this limit is equal to 1, therefore it diverges. Okay. If you use the limit comparison test when they haven't asked you to, I don't even know what to say to you. Okay, so let's see where we're at on this flow chart. I used all my easy things. None of them worked. I went to see if I have any negative terms, right? If I did, I threw them away, and I'm over here in the comparison test. Notice that your rectangle, I have comparison tests and no need for comparison tests. I like these ones better. So I have 2 comparison tests, limit comparison and direct comparison. As I said, please put a little star or something next to limit comparison because AP can make you use that. They can't ask you directly to use direct comparison, but they reserve the right to ask you directly to use limit comparison. Okay. In the next video, we are going to talk about the tests that go under here, the no need for comparison tests. These are the better ones, for the obvious reason that you don't have to come up with a series to compare it to. And that in itself is a gift. All right, so I am sorry about the direct and limit comparison tests. I really am. I promise that it gets better. It gets so much better. Okay. Questions at the end of the video? See you soon.